handled equations, some easy, some hard. And you've handled fractions, lots of them. Now it's only a short step to handling equations with fractions, and you'll be doing it by the end of this module. We can start right now with the first of these two problems. It's an equation, it has fractions. Our goal, get rid of the fractions and then solve the equation. Our method, first find the lowest common denominator of all the fractions, then use it to rewrite the equation without any fractions. The LCD is 21. So we multiply both sides of the equation by 21, every term. That keeps the actual value of the two sides unchanged, but it lets us cancel out the denominators and get rid of the fractions, which gives us a much simpler equation. We can simplify and solve it now with no trouble at all. And notice that our expression on the right can take either of two forms. They both say the same thing. Good news, we haven't done a thing here that we didn't already do before. You already know the technique, and you can use it now to solve this problem. I treat this one just like the last problem. Find the LCD, 30, multiply both sides by 30, every expression, cancel out, and take what I get. What I get is a very simple equation, and I simplify it a little bit more and have my answer. If any of this is confusing at all, take a look at the modules on linear equations to refresh your memory. There's one possible kind of confusion, however, that we're going to handle here and now, because if you fall into it, you're in real trouble. Watch this one closely. Here's a problem, an equation with an equal sign. We saw it a few minutes ago. The first thing we did was to find the LCD and use it. Now, here's a different problem that looks much the same, but there's no equation, no equal sign, just an expression we want to simplify. How do we do that? We find the LCD and use it. Now, do we use it the same way here as we do in solving an equation? Absolutely not, because our goals are different in the two cases. Go back to the equation. It's different. It has an equal sign. In the equation, what do we want to do first? We want to get rid of the fractions. So we find the LCD, multiply every term on both sides by it, and cancel out all the denominators to get rid of the fractions. We saw that when we did the problem. Notice that in an equation we use the LCD to get rid of denominators by canceling. Now go back to the expression. No equal sign. When we simplify an expression, we use the LCD in a different way for a different purpose. Here we don't want to get rid of the denominators. We can't. All we can do is make all the denominators the same, so we can go ahead and add or subtract the numerators. How do we do that? In this case, we make a fraction which is equivalent to x over 7, but which has a denominator of 21, and a fraction equivalent to 2x over 3 with the same denominator, 21. If you have any trouble with that, you can check it in the module on adding and subtracting algebra fractions. But the important thing here is that we're simplifying an expression. We're making the LCD, 21, the denominator, and we end up with a fraction. The LCD does not disappear. In other words, with the equation and with the expression, we're doing two entirely different things. In the equation, we multiply, cancel, and get rid of the denominators. In the expression, we make equivalent expressions, add or subtract, and keep the LCD as denominator. The two are totally different. Don't confuse them. Now we're ready to look at a more complicated kind of equation, one with the variable in the denominator. Once again, we start with the LCD. The only difference is that now the LCD includes the variable, but it will still work in exactly the same way. But before we see that, let me point out one important limitation we have to be aware of. Way back in early algebra, you learned that you can multiply both sides of an equation by the same number, any number, except 0, because 0 would destroy the whole equation. Notice what that means in our present problem. What are we about to do now? Multiply both sides by our LCD, 2x. But think of this. What if x were 0? We'd be multiplying both sides by 0, and we can't do that. So we understand immediately that 0 cannot be the solution to our equation. That's reasonable, of course, since our equation doesn't even make sense with 0 in the denominator. I hope you also understand why the LCD is 2x here instead of 2x squared. 2x squared would be much harder to use, and it's unnecessary. 2x does just what we want. It cancels out our denominators and leaves us a simple equation. We make it even simpler, and we have our solution, 7/10. And since 0 is the only number we couldn't have as our answer, 7/10 is fine. Now let's try an example that shows why we have to be careful about whether the denominator is 0. The LCD is 3x, so again, 0 cannot be a solution for the same reason as before. We can't multiply both sides by 0. Once again, we multiply both sides by the LCD so that we can cancel out the denominators and simplify the equation that gives us, until we end up with the one unacceptable answer, x equals 0. What does that mean? It means that there is no solution to our equation. The equation doesn't have a solution. Now it's your turn. Find the solution to this one. Remember to use the LCD and to reject any answer that would make the LCD 0, because that won't work. I find the LCD immediately by multiplying the denominators together. That tells me that x cannot equal either 0 or 1. If x were either 0 or 1, the LCD would equal 0. Check it out and you'll see. I multiply both sides by the LCD, simplify, and find that x equals 3, which is not either 0 or 1, so my answer is fine. I've got it, and I hope that you did too. Equations with fractions are used in most of the same places as equations without fractions, in solving lots of word problems, in systems of equations, and in solving formulas for one variable. Let's try a word problem. You're in a big department store. The escalator is moving. There is no one on it, and no one is watching. You quickly discover that it takes you 3 times as long to run down the up escalator as it does to run up the up escalator. The escalator is 20 meters long, moving at a steady rate, and you know that on your own you run at 2 meters per second. Question: how fast is the escalator moving? Think about this now and see if you can translate the English into algebra and set up an equation to solve. First, remember the distance, speed, and time formulas. Dover soles are tasty, or Denver steaks are tender. Think in terms of those formulas and use these hints. The 2 is the 2 meters per second that you run on your own. Stop the tape now. I thought about it like this. First, running up. You're going with the escalator, moving faster. Add the speeds together. Then compute time as distance over speed. Then, running down. You're moving against the escalator, moving slower. Subtract the speeds. Compute the time by the same formula. Then I bring in the relationship between the two formulas. That's what makes it an equation. And of course, it's an equation with fractions. Solve it for x. As always, I start with the LCD, which I find by multiplying denominators together. I notice in passing that x cannot equal plus or minus 2, or we'd have 0 for an LCD. Then I multiply both sides by the LCD in order to get rid of the denominators. I do that by canceling, multiply out, and then solve the linear equation. The answer is 1. The escalator moves upward at 1 meter per second. In your textbook, you'll find lots of other problems like this. The best time to look at them is now. And then find some to do on your own. You won't have far to look. Good luck.